Hello everyone, my name is Graham Hedrick, a developer at Q&A. Over the last few months, I migrated our question and answer website from a traditional server setup to a fully serverless one at Amazon Web Services. My goal is to present the tech details clearly, but still understandable for anyone in business leadership. Here's the path we'll follow. First, we'll look at how Docker and Compose was used for containerization to give us a clean starting point. Second, I'll show how I detached the Angular UI from any web server and dropped it into an S3 bucket fronted by CloudFront. Third, we'll unpack the backend transformation by replacing Express and MongoDB with an API gateway, Lambda functions, and DynamoDB. Finally, we'll wrap up with the real-world benefits we observed in security posture, pay-for-use costs, and automatic scaling. Containerization was our first milestone. We wrapped each tier, the Angular frontend, the loopback API, and MongoDB inside its own Docker image. That lift and shift method provided us with a clean foundation. From there, we broke the monolith into small, stateless services that can scale or update on their own. This presents the most beneficial aspect of Docker's immutable pipeline. Build an image once, run the exact same image in testing, staging, and production. If it works on one box, it works everywhere. No more, but it ran on my laptop headaches. To enable that workflow, we rely on three core pieces of tooling. Docker Engine gives every developer the same lightweight runtime, so an image behaves identically on Windows, Mac OS, or Linux. A Docker file is just a text recipe. Choose a base image and add dependencies, copy code, set the start command, completely repeatable and kept in source control. Finally, a container registry such as Docker Hub or Amazon ECR stores those version tagged images. CI pushes in any environment can pull the exact digest it needs, guaranteeing consistency from laptop to the cloud. Once each service was containerized, Docker Compose became our local mini cloud. A single YAML file launches the Angular UI, the Loopback API, and MongoDB with their ports, volumes, and private network, so every developer runs an environment that mirrors production. From there, GitHub Actions pipeline carries the images to the rest of the way. On every push to main, it checks out the code, builds the Docker images, runs our test suite inside those images, tags each one with the commit SHA, and pushes them to the registry. The whole path from keyboard to deployable artifact is repeatable, hands-off, and completely traceable. This visualization ties the previous slides together. On the left, we have three Docker containers, Angular, the Loopback API, and MongoDB, running on a developer laptop. The arrows illustrate our migration path. First, we wrap those containers with Docker Compose for local orchestration. Then, we lifted each tier into purpose-built AWS services. The static Angular build is pushed to S3 and served globally. The API logic moves into AWS Lambda, fronted by API Gateway. And the data layer transitions from MongoDB to DynamoDB, giving us fully managed scalability. This step-by-step journey, containerize, compose, then replace each container with a native cloud service, sets the stage for the serverless world we'll cover next. Once each tier was containerized, Docker Compose became the easy button, so to speak, for local orchestration. A single Docker Compose.yml file describes everything: images, ports, named volumes, and an isolated network, so the environment lives as code. With one command, Docker Compose up, the tool builds any missing images, wires the network, and boots the services in the right sequence using depends on and health checks. When we finish coding, Docker Compose down cleans up just as quickly. This repeatable workflow lets every developer spin up an identical stack in seconds, paving the way for our later move to AWS native services. Docker Compose provides environment parity. The exact Docker Compose YML that starts the stack on my MacBook also runs in our GitHub Actions pipeline. If we have to simulate heavier traffic, we can tell Compose to start several API containers instead of one, all on the same private network. When we move to production, we don't touch that base file. We add a small override that supplies the real database endpoint and the environment variables, passwords, keys, and so on, that shouldn't live in source control. The screenshot shows the base YAML with just three services: the Angular frontend, the API container, and a local development database, plus the internal networks and volumes Compose creates for us. Now that our containers run reliably, we can go a step further and remove servers entirely by shifting the business logic into AWS Lambda. With Lambda, we simply upload a function in AWS provisions runtime instances automatically, scaling them up during traffic spikes and right back down to 0 when idle. This is important because we're built only for the milliseconds of actual execution. Because there are no VMs or OS patches to manage, our operational burden shrinks dramatically, and the team can spend far more time shipping features instead of babysitting the infrastructure. For static assets, we replaced on-premises hard drives with Amazon S3. S3 is object storage that scales automatically and replicates data across multiple availability zones. By contrast, a local disk sits on one machine, offers limited capacity, and will eventually fail, forcing manual backups. Another benefit is S3's elastic billing. We pay only for bytes stored and requests served, whereas physical disks require upfront capital and periodic replacements. Finally, S3 objects are reachable worldwide through HTTPS and can be locked down with fine-grained IAM policies, while a local disk is tied to a single host and relies solely on operating system permissions. To expose our business logic, we fronted each Lambda function with Amazon API Gateway. This combination is inherently elastic. If traffic spikes, new Lambda instances spin up in milliseconds. When demand drops to 0, we pay nothing. API Gateway also gives us production-grade features out of the box: HTTPS certificates, per-client throttling, and full CloudWatch logging. Security is centralized also. We can protect each method with IAM roles or Cognito user pools without writing extra code. All of this lets us focus on features, not the server maintenance. Here's a summary of what happens behind the scenes on every server call. First, the browser hits API Gateway over HTTPS. Gateway converts that request into a JSON event object and invokes the configured Lambda. Inside Lambda, we execute our business logic, typically a CRUD operation on DynamoDB, and build a response object. Lambda returns JSON plus HTTP status. API Gateway transforms that back into HTTP response and sends it to the client. The whole exchange is stateless, fully managed, and finishes in just a few hundred milliseconds. All the serverless logic is just code. We wrote 5 Lambda handlers: table scan, get single record, 2 upserts, and delete record, each in a small index.mjs file using the DynamoDB document client. To authorize them, we created one tight IAM policy that grants DynamoDB, but only on the question and answer tables, and attached it to the common Lambda role. That's the entire backend, 5 scripts, and a single JSON policy. After deploying the API to a stage called API, I copied the invoke URL and dropped it into environment.prod.ts. The screenshot shows the 2 loopback config calls I added in main.ts. A fresh function build and a quick upload of the dist folder to S3 instantly updates the public site, which now calls our serverless API. Next, let's compare our 2 database options. MongoDB is a classic document store. Every record is just a JSON document, and each document in a collection can have a different shape. If I need a secondary index or even a cross-collection join, I can add those at query time with operators like lookup. The flexibility worked well on my local mean stack. DynamoDB, on the other hand, pushes me toward a single table key value mindset. Every item must include a partition key, our ID, and I can add an optional sort key for composite access patterns. There are no joins. Instead, I design access around fast key lookups and lightweight filter expressions. The payoff is built-in elasticity. Read and write throughput automatically scale, so I never have to resize a cluster. So while Mongo lets me model freely, DynamoDB rewards a little upfront scheme discipline with massive hands-off scalability that fits the serverless philosophy. Here's how those data-driven model rules translate into real queries. First, table scan gives us an all-rows view. We can pass a category select to keep it lightweight. Second, get single record is the fast path key lookup. Provide an ID, and then DynamoDB returns the item in a single MS. Third, find one question handles friendly URLs. It filters the question slug, and because DynamoDB has no joins, the Lambda does a second query to fetch related answers and stitches them into the response. Write operations use conditional upserts. upsert question, and upsert answer, so the same code path inserts new items or updates existing ones without race conditions. And finally, delete record removes an item with its primary key. Together, these 5 Lambda handlers cover the full CRUD surface for both tables in an entirely serverless, auto-scaling fashion. As for security, we apply least privilege IAM roles, meaning every principal gets only the permissions it needs, nothing more. The developer console is locked behind a multi-factor authentication, and Lambdas assume short-lived STS tokens instead of hard-coded keys. If we expose this app publicly, we layer Cognito on top to handle user signups and federated logins. Think of an IAM role as the actor and a policy as that actor's script. When Lambda spins up, it assumes a role, which in turn carries one or more permissions policies. I wrote an inline policy named Lambda Access to Question and Answer table that grants only get item, put item, update item, and delete item on our 2 DynamoDB tables. If the role is reused elsewhere, the least privilege boundary still applies. API and Lambda use a trust policy, so only the gateway stage can invoke that function. On the gateway side, we attach a resource policy that whitelists our CloudFront distribution, sealing off any direct hits. Database credentials are stored in Lambda environment variables encrypted by KMS. The S3 web bucket is public read but denies put delete, and each Lambda response injects the correct CORS headers so browsers can call the API safely. To wrap up, let me highlight 3 takeaways from this migration. First, we have seen that a containerized full-stack app can be incrementally refactored into a fully serverless workload. Static Angular in S3 and CloudFront, Lambda for logic, API gateway for routing, and DynamoDB in place of Mongo. Second, those managed services give us true elasticity and pay-as-you-go model. Capacity scales instantly with demand, and we only pay for the milliseconds, reads, and storage we consume. That's a game changer for startups watching their burn rate. Thirdly, we have applied security by design, least privilege IAM roles, resource level policies, and CORS headers. So even as the app scales globally, access remains tightly controlled. Together, these points show how AWS serverless simplifies operations, reduces costs, and sets a solid foundation for future growth. Thank you all for your time and attention for this presentation.